Sir, we can hear you.
Yeah, just wondering, can I start sharing the slide?
Yeah.
Yes, I got it. So I'll be the first speaker today, right?
Yes, sir. You will be the first speaker.
Okay.
Okay, sir.
A very warm good morning to all the delegates and participants present. Today, we mark the second day of the International Conference on Material Chemistry and Catalysis. On behalf of ICMCC Committee Members 2021, I welcome you all once again wholeheartedly. We are going to commence the third technical session, which is inclusive of 7 speakers. At the very onset, we are honored and privileged to have amidst us today Professor Debobrat Maiti as the first speaker of today's technical session. Professor Debobrat Maiti is currently serving as the Associate Professor, Department of Chemistry, IIT Bombay. His research domain basically focuses in the arena of metal catalyst CH functionalization, bio-inspired photocatalysis, and heterocycle synthesis. He pursued his PhD from Johns Hopkins University, USA, and carried out his postdoctoral studies from MIT, USA. He has many credentials to his credit. He is the Associate Editor of the Journal of Organic Chemistry, Fellow of the Royal Society of Chemistry, Editorial Board Member of Chemistry, a European journal. He is the Editorial Advisory Board Organometallics, International Advisory Board of Chemistry, and Asian Journal. Now, I request Sir to kindly deliver his talk. Sir will be delivering his talk on the topic photo-induced regioselective manipulation at proximal and distal sites. Sir.
Thank you very much for your kind introduction. It has been a pleasure to be here today. I hope my slides are visible. Can all of you see my slide?
Yes, sir, it's visible.
Okay, sure. Thank you very much. It's it's early morning for all of you, I believe. So hope all of you are doing great in this extremely difficult time. It would have been nice to visit in person, but given the situation, this is really the best opportunity that we can have. I look forward to visit in person in near future. So today I will discuss part of the ongoing research work in my laboratory at IIT Bombay. Well, we are mainly synthetic chemists trying to work in the domain of organometallic chemistry as well as organic chemistry. It's the interface of inorganic and organic chemistry. Essentially, we look for preparing complex molecule from simple ones. This is a job that is done in nature on a regular basis. If you take a organic molecule at a particular site, natural enzyme will be able to do a particular functionalization. For instance, in these slides, you see cytochrome P450 in front of the iron porphyrin active site. The organic substrate is oriented in such a fashion so that despite having many different carbon-hydrogen bonds, selectively one and only one carbon-hydrogen bond is getting functionalized. So you may be having many different carbon-hydrogen bond into the molecule, but enzyme ensures that a particular carbon-hydrogen bond gets functionalized. Well, can we do such reactions selectively as well as efficiently in synthetic setup? This is a huge challenge for synthetic chemists all across the world, and we simply do not have a clear solution. In last 2 decades or so, what we have seen that there exists a number of literature now or increased amount of activity in the domain of carbon-hydrogen bond activation. Why is that? That is simply because there cannot be any better reaction in anywhere in synthetic chemistry which is better than carbon-hydrogen bond functionalization. It can be greener than everything else. That starting material is cheaper, readily available, large quantity available. But what is the problem? The problem simply is, as I was trying to tell, enzyme can do the reaction selectively at a desired position, but synthetic chemists cannot. And this is particularly why a ligand or a directing group is attached with the organic substrate, as you see in the right hand side, and the metal which will be bound with the ligand or DG or template, basically ligand which has heteroatom, and it can dictate the term where the metal will be positioned. Well, it's not an easy job as it may sound easy. As you can imagine, exactly similar type of pattern is going on in enzyme with respect to the organic substrate metal orientation. Let me take you quickly to this simple journey. Well, these are amino acids. All of us are familiar with amino acids. Amino acids is the building block of life. If we can functionalize amino acid, that will be wonderful. Well, amino acids, both amine as well as carboxylic acids, can be the ligand for metal. As I was discussing, we'll be focusing mainly on organometallic, organic, organometallic, inorganic type of chemistry, right? Well, is there any method that exists which can functionalize such amino acids? Simply, there are not many, or there was none, to, let's say, functionalize this gamma CH bond, which I have highlighted here. Amino acid can have alpha, beta, or gamma CH bond, right? Let me show here. So this is an alpha position, this is beta position, this is gamma position, this is delta position, right? But how can you selectively, let's say, for example, at the gamma position, do a reaction? Metal can bind over here, or metal can bind over here, but it will not be directed very close to this gamma position selectively. Even metal can bind in a bidentate mode, still things will not be happening. So this is where we thought that we will bring a better ligand. We'll bring a ligand, simple ligand such as this 8-aminoquinoline, and will attach on the acid unit. If we are able to do that, then there might be a possibility that metal will be coming very close vicinity of this CH bond. So once metal is bound or interacting with this CH bond, then you can have a organometallic intermediate where metal is inserted and a metal carbon bond is formed. If that's the case, you can do an organometallic reaction pretty efficiently to give these products. Well, as it turned out, this is a general approach, and we are able to selectively functionalize this gamma CH bond, and this reaction works quite well with very good levels of stereoselectivity, good to moderate to good to excellent yield in selective cases. So the major advancement has been that at gamma position of acid, it could be amino acid or simply other acid, gamma position selectively, we can form new bond without touching alpha, beta, delta, or any other bond that is present in the molecule. This is once again similar to what we see in enzyme, but by doing so in synthetic setup, we can certainly synthesize molecule which can be used in industrial sector as well as in academia. These are once again simple amino acids, cheap, readily available, and very, very useful for life. Well, you may be wondering, of course, amino acids are not limited to alpha, beta, gamma position. There is also a delta position, right? Can one selectively functionalize delta CH bond without touching alpha, beta, or gamma position? These are again Very challenging task, quite exciting, and there exists no solution for such problem. Once again, the challenge is how can you promote these reactions selectively at the delta position without touching alpha, beta, and gamma positions. These alpha, beta, gamma positions are easy to do the reaction with because these will form kinetically as well as perhaps thermodynamically more preferred product. So promoting the distal position such as this delta position reaction selectively, okay, efficiently, selectively, absolutely selectively at this distal position without doing any reaction at this position is always going to be challenging. Here we have introduced this pyridine carboxylic acid, as you can see, simple pyridine carboxylic acid on the amine unit. Previously, we were introducing the ligand from outside, that is 8-aminoquinoline with acid. Now we have introduced this pyridine carboxylic acid as this amine unit, and we see that reaction can be done selectively at the delta position because metal is getting inserted selectively at the delta position. So delta CH activation happens and metal inserts, and then the reaction happens quite efficiently. Not only one arylation, you can keep on doing again and again and again. Iterative arylation can be done efficiently. One of the limitations is that we have to introduce a ligand. Usually, as you are seeing, we have to introduce a ligand like this pyridine carboxylic acid with the organic substrate. Okay. Now, can we do this reaction simply on the acid without introducing a directing group or ligand with the acid by utilizing the acid as a directing group itself? This is a weakly coordinating or weakly coordinating ligand for the metal center. Can acid itself direct? Yes, it is possible, but of course not in every cases. This is a selective such cases where we were able to show that acid can direct the functional ideas. For example, in this case, arylation reaction can be done with acid. We can do one arylation, even two arylation. All these cases, simple acid can do the reaction. Okay, so what have we learned so far? We have learned that acid or amine substrates can be incorporated for a particular reaction. We have shown a number of functionalization very quickly as well. For a particular reaction, selectively at a desired position, let's say at gamma position or delta position, or even further, perhaps we did not show that. Also for alpha and beta, these are known. Proximal positions such as alpha position, beta positions are not that difficult. But the gamma, delta, which are distal positions, are usually challenging. And we hope, briefly, I was able to tell you that how taking advantage of a ligand which is well designed or strategized perfectly to be attached with the organic substrate, the reaction can be done. Also in the last plot, this slide I show, you do not have to necessarily add ligand all the time with the organic substrate. It is possible to attach, without attaching the ligand, you can still do the functionalization, provide the substrate is suitable even at the delta position. Okay. Now that was aliphatic substrate. Let me change a little bit the topic for aromatic substrate. All of us have studied in our undergraduate study that ortholithiation can be done with a suitable ligand, metal ligand on the organic substrate. So if you have a suitable directing group or ligand, let's say phenol this is or aniline this is, then metallation can be done at the ortho position by virtue of 5 to 7 membered metallocycle formation, like ortholithiation, right? But can we do a similar reaction at the meta position? What is the problem? Problem is how are you going to prevent the ortho-CH functionalization? Of course, there are two different ortho-CH bonds which can potentially get functionalized. How will you deliver metal directly at the meta position without activating the ortho position or even the para position? That is the challenge. Okay, to keep it very short, what we were able to do is to design ligand for the organic substrate. So the brown color part is the ligand for the organic substrate, which is black in here. So this is the organic substrate. The brown colored part is the directing group. In every cases, as you see, as long as we introduce this ligand within the organic molecule, metal will be bound with this ligand and metal will interact with this CH bond selectively. Just like what you have seen in ortholithiation. This is like selective meta activation or metallation at the meta position. What is required? You need a ligand which is in brown here, the cyano-based ligand to be precise, and this metal then will bind with the nitrogen and will be placed in such a way so that meta CH bond can be activated. As you can see, a number of reactions can be done. Actually, something like 15 different reactions we can do now. Okay. Well, what we find here, this is the reaction mechanism where you see the nitrile-based ligand or cyanophenol-based ligand is attached with the organic substrate in such a way so that only the meta CH bond is exposed towards the metal center. Ortho as well as para CH bonds are not getting interaction with the metal center, or predominantly this is the one which is getting activated. Okay, just going back again. So the organic substrate or the ligand is attached with the metal center, and it is orienting in such a way so that meta CH bond is getting activated. Once again, to bring the enzyme reference, enzyme does exactly same thing, that the substrate is perfectly oriented in front of the metal center in the metalloenzyme, and therefore only one CH bond into the organic substrate gets activated and then subsequently gets functionalized. Okay, so the reaction, of course, we understand the reaction mechanism in greater detail, both by experimental studies. Many experimental studies have been done and many computational studies have been done to understand the reaction mechanism in greater detail. Okay? So we believe that this is the reaction mechanism. A simplified version I am showing is happening here. Okay, now maybe I'll go a little faster. One of the problems that we were facing is that we are depending on nitrile to hold the metal perfectly so that functionalization happens at a desired position. As you see in the last slide, so the nitrile is holding the metal perfectly so that functionalization happens directly at the meta position. And that's how the ortho as well as para CH bonds are not getting activated. Well, as you know, the nitrile is not a strong ligand. It's a weakly coordinating ligand. It is acid, base, and reducing condition sensitive. And more importantly, it's a monodentate ligand, right? Therefore, the metal cannot be bound with the nitrile effectively. Right? That's a problem. That's a huge problem. How do you overcome such problem? Okay? To overcome such problem, you need to have a stronger coordination. You need to have a better ligand than nitrile. Of course, the metal positioning should not be complicated or should not be compromised. So we needed a stronger coordination. Something in our lab, we call it 1.5 coordination. One strong coordination and another weak coordination. As I said, nitrile is weakly coordinated. Slowly we are moving from a 1.5 coordination, one strong coordination and another weak coordination. When we arrived at this 8-nitroquinolide, reaction becomes little bit room temperature, broader scope, high yield and selectivity. But one thing you have noticed from the cyanophenol, we have arrived at this point where molecular weight is high. We don't want ligand to be very bulky or big because we want to commercialize them. We want to have this from market. And of course, not that many reactions were working with this ligand, and that is why we started working towards a better ligand where we arrived at this biphenyl pyrimidine based ligand, which is turning out to be the best in the literature so far, better than anything else that is out there. And that is because this ligand over here can bind with the metal center more precisely than anything else for this purpose. It is a better sigma donor as well as pi acceptor, something which you see even in the metal carbonyl complexes, right? This ligand metal complex is so good that it can hold tightly on the metal center without compromising the denticity. It's a monodentate ligand. Why we need monodentate ligand? Because we are usually dealing D8 metal center in the palladium 2 oxidation state, for example. You have a square planar geometry. So if you have too many denticity, or let's say if you have bidentate or tridentate ligand, the number of coordination site is really compromised. The reaction, the organic reaction that we are looking at, will occupy some coordination mode as well. So it's better to keep monodenticity, okay? And of course, there exist a number of other designing aspects that is going on with this brown color directing group, okay? Let me first tell you, if you really want to remember anything at all from this talk, I would say, please do remember this brown color species, right? This is turning out to be the better than anything else that is out there, okay? So with this brown colored ligand, we see that it has a number of features that is making it better ligand. What are those? Well, you have 2 nitrogen, so the statistically you have higher probability of finding palladium and placing it in front of the meta CH bond. You have hydrogen bonding with the solvent, which is hexafluoroisopropanol, which is also assisting in carbon-hydrogen bond activation. You have free rotation, which is also assisting in positioning the metal with respect to the organic substrate. Preferably, you have Thorpe-Ingold effect, which is bringing the organic substrate as well as ligand to the close vicinity of each other. With this ligand, previously unsuccessful reactions such as alkylation, cyanation can be done. A series of small natural products as well as agrochemical and pharmaceuticals can be synthesized by utilizing this method. Well, one of the things that was also happening that with this ligand, now we have an opportunity to make the carbon-hydrogen bond activation step reversible as well as not the rate limiting step. As you can see over here, this step, which is the key step, that is the carbon-hydrogen bond activation step, is no longer rate limiting and it becomes reversible. If that's the case, we can introduce the deuterium by utilizing a D plus source, deuterium plus source, like deuterated acetic acid, let's say. We can introduce the deuterium selectively at the meta position of the organic substrate. This is quite exciting because there are a number of drugs molecules where one would like to introduce such deuterium labeling. This is one of my favorite slides, which is essentially says that, or the answer the questions whether, irrespective of the organic substrate, if we have this template or ligand or directing group, whatever you want to call it, if we have this template attached with the organic substrate, irrespective of the linker length or the type of linker, we can still get the meta-functionalization. You see a variety of functionalization, olefination, alkylation, acetoxylation, cyanation, all can be done in good to excellent yield and good levels of selectivity. Okay. Very recently, we were able to show that even most difficult or one of the most difficult reactions, such as incorporating unactivated internal olefin, can be done as well, and selectively exclusive E product we are getting, and that's again with the same ligand, that is biphenyl pyrimidine based ligand, it is doing the chemistry. We can do the inverse Sonagawa-Chirac type of reaction. Once again, a very exciting reaction with the help of CH activation. So the meta-CH bond is selectively activated, and with an alkynyl halide, we can do the meta-alkynylation reaction. A number of drug molecules, pharmaceuticals, agrochemicals, and pesticides, all can be incorporated or decorated with the meta-alkynyl group. Well, yet another exciting reaction is the Shoji-Trost type of allylation reaction, but at the cost of CH bond, which is excellent in terms of its efficiency. And we can do this allylation reaction with moderate to good levels of yield as well as selectivity. Well, let me change the gear quickly and come to another related topic, and that is how are we selectively achieving the metallation at the para position. Once again, the challenge is simple and same. That is, ortho-CH activation is preferred. Meta-CH activation can be done, as I have discussed in last few slides, with a suitable template, cyano-based or biphenyl pyrimidine-based template. You can achieve the metallation at the meta position. But how to bring the metal to the para position? This is something not known at all in the literature. For the very first time in the literature, we were able to show that with a suitably designed ligand, we can now place the metal at the para position without touching ortho position as well as meta position. So this is again going back to the textbook, let's say undergraduate study, our bachelor studies, where we have been told that let's say electrophilic aromatic substitution can be done at the ortho position as well as para position, and the nucleophilic substitution can be done at the meta position. So depending on the organic substrate, you will get a particular type of reaction. What we are trying to tell here you is, it doesn't really matter what type of benzene ring you have and what type of reaction you need. You can do every reaction at every position, be it at ortho, meta or para for aromatic substrate, similarly for aliphatic substrate as well. So that's the power of organometallic chemistry or this directing group approach for this sort of reaction. So in this case, for example, we are able to promote the olefination selectively at the para position. So we see that selective olefination can be done at the para position. This is the crystal structure showing clearly that from the organic substrate template is coming and wrapping it up so that olefination can be done at the para position. Okay, moving on. Well, of course, one of the problem was we could not do the functionalization very efficiently without this dimethoxy group, and there are a number of problems if we substitute things at any other position. Very recently, we were able to show that by having this dimethoxy substituent, we can get a second generation template which is going to be much better in terms of selectivity, yield, and functionalization. Of course, there is hydrogen bonding from a hexafluoroisopropanol solvent, which makes the reaction better. With this ligand, second generation template, which is essentially have dimethoxy group, we can do these reactions with very good yield and moderate to excellent levels of selectivity. The reaction mechanism is relatively simple, as you may have imagined. The metal is bound with respect to the directing group in such a way so that metal is positioned perfectly with respect to the para-CH bond, and it's getting activated and metallation is happening selectively at the para position. This is the crystal structure of the substrate, which clearly shows that metal will be positioned here and will activate the CH bond just preferably here. Okay, the ortho as well as meta-CH bond doesn't get activated. Okay, and very recently we were able to show that both rhodium can be active at meta as well as para position. I think I'm coming very close to my time. So just to summarize this part then, I will not discuss really photochemistry today. What I hope I'm briefly able to tell you is, if you have a ligand for the metal center, which we are calling as a DG or directing group or template, if you design this suitably, you can place the metal with respect to the DG perfectly so that meta-CH bond selectively gets activated. For this DG, you can use this one, which is now commercially available with Aldrich. If you want the best ligand, as I was telling you, this is the best DG or ligand. So this is the best one so far for the meta-CH bond activation. If you want the para-CH activation or para-CH bond functionalization and any reaction, let's say at the para position you want to do selectively without touching ortho as well as meta-CH bond, you don't want any reaction here or here or here or here. You just want the para-CH bond to be activated, then these are the first generation template. This is the second generation template that we are looking at. I'll skip it and I'll just summarize it. I hope briefly I'm able to tell you that with a suitable directing group, if you are ready to introduce within the organic molecule, you can do the functionalization at the meta position. With a suitable directing group, if you are interested in doing the reaction at the para position, again, the metal can be placed perfectly with respect to the para position and you can do the reaction efficiently. Of course, we are trying to overcome a number of limitations that we have seen so far that maybe can be discussed on another meeting. Let's hope that let me hope that I'm briefly able to tell you that it is possible to do these reactions selectively at a desired position, both at aromatic substrate as well as aliphatic substrate. As you have seen, the design of the directing group is different for aliphatic substrate. These are difficult substrate. And for aromatic substrate, of course, these are also difficult. The design of the directing groups are different. Okay, let me thank my students. Of course, let me skip the slide. Sorry for that. Let me thank my students who has done all this job. I'm happy to be there with them, but they are the one who has designed the reactions very efficiently and have taken a lot of pain and experimental trouble to reach the efficiency level that we have. Here we have JP or Jyoti Prasad Vishwas. I think he is in the job market right now looking for a faculty position. I think he has applied to Tezpur University very recently. So he is an excellent student. So if you have a suitable position available, please do consider his application. And of course, thanks to the funding agencies, all the funding agencies, DST, SCR, BBRNS, CSIR, for their constant support. Without that, it will not be possible to any exploration studies, and our collaborators and all the alumni for their support. Thank you very much. I'll be happy to have your question if time permits. Thanks for listening. I hope to see you soon in person. Stay safe, stay happy. Thank you very much.
Thank you, sir, for your informative talk. The session is now open for questioning and discussion purpose. If anyone have any queries, you can unmute yourself and ask your question.
Thank you very much, sir, for your excellent talk. You make this complicated reaction in a very simple way. So just I have one query. In your many template of DZ groups, if there is a flexible rotation through single bond or like that, so is it an advantage or sometimes it may have some problem?
Absolutely, this is a great question. Of course, can some of us mute? Okay. The problem is if it is having too much flexibility, of course, we can end up seeing the selectivity issue. If it is flexible, that means the positioning of the metal with respect to the organic substrate may not be perfect. So we don't want way too much flexibility, but at the same time, if it is not flexible, it may not reach to the target position selectively, right? So I think it's a somewhere the sweet balance between the flexibility and some sort of rigidity. The things that I did not also or could not discuss, that there is another pi stacking interaction that is going on between the directing group as well as organic substrate. So these sort of interaction, pi stacking interaction between, let's say, arene ring of the organic substrate and the arene ring of the template or the ligand, right? These pi stacking interaction is also helping in stabilizing this sort of orientation. Okay, so it's not only one factor, there are multiple factors that's put together, which I may not have discussed in detail. Put together, we are able to achieve the selectivity. Okay, to answer your question directly, I think we need rigidity as well as flexibility, but with a moderate amount. If you have too much flexibility, selectivity would be difficult, or metal will not be really positioning perfectly with respect to a particular position. If you have too much rigidity, then the orientation will not be really proper, so that maybe will not be able to go to the desired position at all. So that could also be a problem. For example, if we make rigid biphenyl ring for the para scaffold, there is no activation at the para CH bond because it's not freely rotated. I hope that answered your question in part.
Yes, thank you very much.
Thank you.
I presume there are no questions, so we will move on with our second speaker. Thank you, sir, once again.
Thank you.
The next speaker we have is Dr. Ilyas Z. Ismagilov. Dr. Ilyas Z. Ismagilov is currently associated with Boreskov Institute of Catalysis, Russia. His research area focuses in the domain of environmental catalysis. His skills and expertise lie in the field of computational fluid dynamics, XRD, development of novel catalysts, and carbon nanomaterials. Sir will be delivering the talk on the topic Role of Structural and Redox Properties of 3D 5D Transition Metal Catalysts in Methane and Carbon to Oxygenates Conversion with Hydrogen Production. With this, I would request Sir to kindly resume his talk. Sir, you're requested to share your slides.
Yes. Dear colleagues, do you hear me?
Yes, sir, you're audible.
Yes, yes.
So please share your slides.
Yes. One moment, please. Okay. Yes, yes, I can hear you. Yes.
Please share your slide.
Yes. One moment. Mhm.
If you find any difficulty, we can help you.
Yes. I'm trying to at the moment. Just a second. Oh, okay. Okay. Sorry. Just one moment, please. Um. Oh boy.
Hello, hello.
Oh, just a second now. Mm, mm, mm. Mm, 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 mm. Mm. Yes, Professor Pankaj, hello. Yes. I'm almost done. For some reason, yesterday it was just fine. Give me please 1 minute. 1 minute. Okay. All right. So yes, 1 minute, please. Yes, I'm opening. Some strange retardation here. Yesterday it was just perfect. Yesterday. Okay. Okay. So yeah. Yes. I'm doing so. Yes. Okay. Mm, 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 oh, mm.
Professor Bean Park, can you hear me? It's Kusum.
Yes, I can hear you. Can you hear me?
Yeah, I can hear. So, sir, can you, because one of the speaker, he's facing certain problem in connecting.
Mm-hmm.
So, will it be possible for you to give your presentation now?
Sure, I can do that. Yeah.
Yeah, thank you very much.
Okay.
Due to some technical glitch, Dr. Ilyas Z. Ismailov is unable to present right now. So the next speaker on board is Professor Young Bin Park. So, yeah, Professor Yangbing Park is currently serving as the assistant professor in the School of Mechanical and Materials Engineering, Ulsan National Institute of Science and Technology, South Korea. Dr. Park's research interests are in the field of advanced composite and nanocomposite technology for development of functional and intelligent materials and structure. There are numerous credentials to his credit. He's the journal reviewer of a number of reputed journals, namely Composite.
Okay, can I start? Can I start?
Yes, sir. Yes,
Okay.
sir.
Oh, sorry. I got disconnected for a few seconds. Okay. Thank you for the introduction. I'd like to thank Professor Kusum Bania for inviting me to this conference. Actually, I have two postdocs working with me who are Tezpur University graduates. So this is a really a great honor and pleasure for me to present my talk. I need to confess first that I'm not a chemist or chemical engineer, but I'm a mechanical engineer. So my research area is quite different from, quite far from catalysts and materials chemistry. So I went through my research portfolio and picked out the topic that is most closely related to chemistry, but still it's quite far from catalysts. But I hope you enjoy my talk because it could be a little bit different from what you might be expecting. So today I'd like to talk about my recent research on composite materials and how I enhance the mechanical properties of composite materials by reinforcing or strengthening the interface between the fiber and the resin, which is a matrix. I think I'd like to start with a very brief introduction of our university as well as our center here. So we are located in Ulsan, Korea, so which is here. And I'm not sure how many of you have been to Korea, but Seoul is right there, which is the capital of South Korea. And Ulsan, our city, is about 4-hour drive south of Seoul. And Ulsan is known as one of the heavily industrialized cities in Korea. So we have a population of about 1.2 million, which is a small percentage out of the entire population of Korea. But Ulsan is a very productive city because we're producing more than 10% of the total Korean annual exports. Our university, UNIST, is a relatively new university. It's one of the what we call ISTs, is the Institute of Science and Technology in Korea, supported by the government. There are 4 IST universities, and we are one of them. We have 4,000 students and more than 300 faculty members. So we are research-oriented and research-focused university in Korea. A little bit about myself. Here's my research field. First of all, my lab is called Functional Intelligent Materials Lab. So my research topics are centered around multifunctional composites and nanocomposites, primarily lightweight materials based on composite materials. My most recent and most heavily researched area has been sensing, structural health monitoring, and energy harvesting, particularly using carbon nanomaterials such as carbon nanotubes and graphene. And there are other functionalities that I looked at. So my ultimate goal is to develop material systems that can think and respond, which we collectively call smart and intelligent. So as you can see, I'm not somebody who creates or synthesizes materials. I bring all these available materials together and design them, put them together, engineer them to make it into a system that can be smart and functional. So I included this slide because it shows the overall research that I have done the past 10 years. And it's centered around using carbon nanomaterials and carbon nanomaterial derived composites for sensing applications. When I say sensing, I particularly mean mechanical sensing, such as strain sensing, crack detection, failure detection, and so forth. So my initial research was on carbon nanotubes and graphene. So in this case, we combined carbon nanotubes and graphene into a hybrid, a freestanding hybrid sheet, which can be self-sensing, meaning if you attach these freestanding sheets on a structure, and when the structure undergoes deformation or some type of mechanical loading, any type of events or failures, then this sensing film can detect all those mechanical events. I worked with a professor in chemical engineering. So she directly synthesized transparent graphene film on an epoxy-based substrate. So it's a little hard to see here, but there is a transparent sensing film which has been directly grown on the epoxy substrate. And when this substrate undergoes mechanical deformation, bending in this case, the transparent sensor can bend, the transparent graphene film can sense and measure those deformations, the flexural deformations. I also worked with a chemist nearby our university, and we developed a graphene-based hydrogel, which has been functionalized and reinforced with platinum particles, nanoparticles. So this hydrogel sensor can sense compression. And finally, this is polydopamine functionalized graphene oxide composites. So in this case, I work with a chemist at our university. So he functionalized graphene oxide with polydopamine, which is a naturally occurring, in this case, synthesized bonding agent, which can help enhance the interfacial bonding between graphene oxide and PVA, which served as the matrix material in this case. So not only polydopamine functionalization promoted interfacial strengthening, but also we were able to use this as a sensor for moisture detection. And then more recently, I'm looking more at a macro scale or micro scale composites, in which case we're looking at how to reinforce, how to produce or how to process fiber reinforced composites for different applications, particularly for structural applications in automotive. So in partnership with Fraunhofer ICT in Germany, we found a satellite center at our site. So we have our own dedicated building here. And here we're doing research on processing and characterization of composite materials. So with that, I'd like to move on to today's topics. I have two parts to present. The first topic has to do with reinforcing the interface between carbon fibers and nylon PA6-based matrix by including or incorporating carbon nanotube modified silane. Okay, silane here serves as a coupling agent between the fiber and the matrix. Also, in addition, we are trying to promote mechanical interlocking by directly grafting or growing zinc oxide nanorods on the surface of carbon fibers. So this is a multifaceted approach for enhancing the interfacial bonding within a carbon fiber composite. In part two, this has to do with both processing and also interfacial strengthening. So in this case, we take polyamide 6,6 as the matrix material and carbon fibers as the reinforcing material. And at the interface, which is formed between the carbon fiber and the matrix, we include graphene oxide and carbon nanotube in a hybrid form, and we do so by using a process called in situ interfacial polymerization. Okay, since I'm not a 100% expert in chemistry, I'm not going to go into great detail because I know you're more experts than me, but I'll just show you some concepts that we used to reinforce the composite. So this is the our very first topic. So we all know that a composite consists of a reinforcing material, in this case, carbon fibers, and the matrix, in this case, it's nylon or polyamide-based thermoplastic. And we know that by experience and by theory that the longer the fiber, the higher the mechanical properties, and so on. But the issue has always been the limitation in the mechanical reinforcement due to the weak interface between the fiber and the matrix. So as a composite engineer, just like any other composite engineers in the world, I have been looking at how we can maximize the adhesion or the interfacial bonding or interfacial strength between the fiber and the matrix. So for instance, if you look at the SEM images below, these are very representative examples of the weak interface between the fiber and the matrix. So in this case, we see a clear separation between the fiber and the matrix. And in this case, we have observed fiber pullout. Okay, fiber pullout is a very, very common failure mode that is observed in a composite where the interfacial bonding is very weak. Okay. And also here you can see a very clean separation between the resin and the fiber here, which also is an evidence of weak interfacial bonding, and same thing here. So the question is, how can we maximize the strength between the fiber and the matrix, which is considered to be the weakest link in composite? So to maximize load transfer from the matrix to the fiber and vice versa, we have tried many different methods. And one method that we thought was very effective was a concept called multi-scale hybrid composite. We call this MHC. So why do I call this multi-scale? Because a multi-scale hybrid composite consists of three components. The resin, which we consider to be macro scale, the reinforcing fiber, in this case, a carbon fiber, which is micro scale, and also nanomaterial that is included somehow, which is at nanoscale. So there are three main ways to include these nanomaterials in a composite. And the most common and the most widely practiced, and unfortunately the least efficient way, is by uniformly dispersing nanomaterials in the matrix like this. So the idea here is by including the nanomaterials, we're trying to reinforce the matrix. However, if you consider a composite as a motion picture, like a movie, the main character is actually the fiber. Okay, so fiber is the one that is providing the greatest load-bearing ability to the composite, and the matrix can be considered to be serving as a binder. Okay, therefore, since the mechanical properties of fibers are several orders of magnitude higher than the mechanical properties of the matrix, even if you reinforce the matrix, it's not going to enhance the overall mechanical properties that much. So this is an old-fashioned and least efficient way. Okay, so I've been thinking how we can deviate from this method and try to maximize the use of the nanomaterials property and let that be reflected in the overall property of the composite. And one way is by somehow concentrating the nanomaterials at the interface, because we know that interface is the weakest link in a composite, and that determines the overall properties of the composite. So if you look at this schematic, the gray circular area is what we call the interface. And within the interface, if we could reinforce the interface with these high-strength nanomaterials, then we may expect that the overall composite property could be enhanced. And the second way is somehow, if we could directly grow these high-strength, high-stiffness nanomaterials on the fiber itself, then this creates a mechanical interlocking scheme between the fiber and the matrix, which we observe as an overall enhancement in the mechanical property of the composite. So in these two topics I'm going to present to you today involves this second and third method. Okay, so I'm going to skip through this slide quickly. So let's move on to part one. Since time is very limited, I'm going to just show you some concept and some significant results. Okay, so there are three main components that are involved in the first topic. Okay, first we surface treated the carbon fiber with plasma, atmospheric plasma, and effectively what this does is plasma treatment creates a hydrophilic surface on the carbon fiber surface. At the same time, it increases the surface roughness. Now, if you have a rough surface on the fiber, then that creates better contact between the fiber and the resin. And the third most important effect is that it increases the polar functional groups on the fiber. Now, these polar functional groups are very, very important because they act as the bonding sites or bonding sites between the fiber and the matrix, and effectively enhancing the interfacial bonding. The second component is what we call viscorization. So, and this is when we grow the zinc oxide nanorods on the surface of carbon fibers. And as I said before, as you can see on these two comparative figures or schematics, on the left-hand figure, you see the black carbon fibers without any surface treatment, without any viscorization. And after viscorization, you see these nanorods vertically grown on the surface of carbon fiber, and they create mechanical interlocking, which leads to enhancement in the mechanical properties of the composite. Okay, so I just explained to you two methods, two approaches: plasma treatment, and number two, viscorization. And number three, this goes back to my previous slide when I showed you reinforcing the interfacial region between the fiber and the matrix. So in this case, almost every fiber are treated with a coupling agent, and oftentimes silane is one of the most common types of coupling agent. And in this case, our intention was to mechanically reinforce the silane, the coupling agent, by adding carbon nanotubes. So in the third approach, we added carbon nanotubes to silane, and which was eventually coated on the surface of carbon fibers. So I'm going to explain this to you in more graphical way. So these three approaches, they combine to have synergistic strengthening effects on the mechanical properties of the composite. So more graphical representations here. So we have initially carbon fiber with the resin, and then this is viscorized carbon fiber with the resin, and then you have finally the composite that contains plasma treated carbon fibers, viscorized, and then CNT modified coupling agent coated on the surface of carbon fibers. So if you look on this side, you have this squiggly feature here is this carbon nanotube. The hexagonal rods vertically grown on the surface of carbon fiber. This is the zinc oxide nanorods. And although not shown here, in the very beginning, the surface of carbon fibers were plasma treated. Okay, so I'm not going into great detail here, but again, I'm repeating. We are treating the carbon fiber fabric or woven fabric with plasma first, and then we grow zinc oxide nanorods by using a conventional hydrothermal synthesis method, which is shown here. And then we create a solution containing the silane coupling agent dispersed with carbon nanotubes. In this case, we used functionalized carbon nanotubes. And then we dip the zinc oxide nanorod grown plasma treated carbon fiber fabric or textile in this silane solution dispersed with carbon nanotubes. And finally, we have fully functionalized and fully surface treated carbon fibers. So we take this carbon fiber, which has been fully functionalized, fully treated, and we place it in a mold like here. And then, again, this is a very unique method that we created, but I'm not going to go into great detail. But here we have the monomer, the catalyst and the activator, and the resin, the monomer, all mixed together. And then it is forced into the mold using vacuum. This is called vacuum-assisted resin transfer molding, but it's a very unique process because we're trying to infuse a thermoplastic instead of a thermoset resin. So this is a very unique process. So moving on, we did some analysis. The first key analysis we had to do was to optimize the plasma treatment condition. So in our case, I want to go back here. When you treat the fibers with plasma, the height between the nozzle and the plasma and the carbon fiber is a very important parameter. And we believe that the nozzle height determines the intensity of the plasma. So we vary the height of the nozzle of the plasma treating equipment. And we did the XPS analysis, and by this analysis, we were able to find which condition or which nozzle height gives the highest degree of oxygen functional groups on the fiber surface. And it turned out that 70 millimeter gave us a very good functionalized surface on the carbon fiber. And we also used AFM to measure the surface roughness, because the higher the plasma power, in other words, the smaller the height of the nozzle, the higher the plasma power and intensity, and that tends to lead to a rougher surface on the carbon fiber. Okay, and also we visually analyze the surface at a micro scale using the SCM images, and here we particularly observed the growth state of the zinc oxide nanorods on the carbon fiber surface. And it turned out that in terms of the density, the height, the growth direction, and the width of the nanorods, around 70 millimeters was the best. And finally, the XRD, this gave us some information on the growth direction of these nanorods, and collectively, summarizing all these analysis results, we concluded that 17 millimeter plasma treatment condition. This 17 millimeters means the height of the nozzle of the plasma system gives us the best condition for functionalization of the carbon fibers, as well as the zinc oxide nanorod growth on the fiber surface. Okay? And we also had to confirm that the silane was properly coated on the carbon fiber. Remember, this silane, which is a coupling agent, contains the carbon nanotubes. And we we want to make sure that the silane is chemically interacting with the nanorods as well as the plasma-treated carbon fibers. And of course, the silane coupling agent naturally chemically interacts with the resin around it. Therefore, this is a four-way interaction, chemical interaction between the silane, the nanorods, the fiber, carbon fiber, and the resin. And in addition to that, we have reinforced the silane with carbon nanotubes. This is a five-way reinforcement scheme. So that's what we confirmed. And then finally, the morphology of the carbon fiber surface showed that a certain amount, under a certain condition, gave us the best coating condition of the silane. Because remember, silane is a coat. It's a coating on the carbon fiber. Therefore, you do not want that coating thickness to be too large. Otherwise, all the nanorods will be embedded in the sizing, and that's not what we want. We want the nanorods to be exposed on the fiber surface. At the same time, we want the carbon fiber to be uniformly and very thinly coated with the silane. So based on this visual or microscopic analysis, we optimized that the best silane condition was by dip coating the carbon fiber with the silane in the range of 10 to 25 milligrams. Okay. And TEM results also showed the thickness. So here we're trying to exactly measure the thickness of the coated layer, silane layer here. And finally, from my perspective as a composite engineer, I want to show how all of these transitions to the mechanical properties. So in terms of the drop weight impact test or tensile test, in-plane shear test, which are all very important properties that are measured for composites, which are intrinsically anisotropic material. The tensile strength, the modulus increased by 41% and 30%. So the increase in these performances is based on the reference material where there was no silane treatment, no plasma treatment, and no CNT, and so forth. And we had a very high enhancement in impact, 179% increase in plane shear strength, and also penetration limit. So we were very, very excited to get these results. And finally, these are the fracture surfaces. So you can see that carbon after the fibers have been removed, you can see carbon nanotubes are exposed. This means that until the last minute, the carbon nanotubes, which were dispersed in the silane coupling agent, they did their job by holding on to the silane as well as the resin. So that's why you see the pull-out of the carbon nanotubes here. So in the interest of time, I need to skip. So I'm going to spend maybe like 2 minutes on this very quickly because I'm running out of time. So the second topic is about using or the reinforcing the interface between the carbon fiber and the polyamide 6,6 resin with graphene and carbon nanotube as the hybrid reinforcements. And then we did this by a coating method called in situ interfacial polymerization. So this is our goal. So we have the carbon fiber here, the resin here, and between the resin and the fiber, we have the interface, which is like a thin layer, which contains the graphene oxide and carbon nanotubes. So please feel free to contact me later if you like these slides, because I need to skip through very quickly. Okay. So what's the key concept here is in interfacial polymerization is on top you have an aqueous solution, which is composed of this here, and then in the lower half you have an organic solution, which is composed of these components and the graphene and carbon nanotubes mixed together. So what happens is, as you pull some of the material here up through the interface into the aqueous solution, that's the interface is where the actual polymerization takes place. So the whitish material produced here is the actual polyamide 6,6 material. In this case, because we have carbon nanomaterials dispersed in the organic solution, in the final polyamide 6,6 will contain the carbon nanomaterials. And we our approach is a little different, because here, instead of just pulling this material over, we're going to pass a roving of carbon fibers starting from the lower phase through the interface, through the upper phase, and effectively what that's going to do is it'll create a carbon fiber roving coated with PA66 reinforced with carbon nanomaterials. So these are all optimization processes that we did in terms of the proportion between the graphene oxide and CNT. And then this is how we tested them. So as a result, we were able to, comparing with a conventional nylon, we were able to enhance the tensile strength, modulus, and strains. It's very difficult to enhance both the strength modulus and the strain, but in this case, we did that. And here, as I just explained to you, we passed a roving of carbon fibers here through the organic solution, through the interface, and through the upper aqueous solution. And finally, we get a nicely coated carbon fiber with a sizing that contains the nanotubes and the graphene. So this is how we made the coatings and how we made the samples here. I'm going to quickly go through. And you can see very, very good bonding between the resin and the fiber. You can see typically if you have poor bonding, you'll see smooth surface of the fiber, but here you see very nice coating. And then ultimately, we got really nice improvements in terms of the interfacial shear strength, tensile strength, and tensile modulus, and so on. And then also in terms of the dynamic mechanical behavior, we got good results. And these are the results. And in the control sample, we have very poor interface between the fiber and the resin, evidenced by this debonding. But with the nanotube or graphene oxide inclusion, we have very good bonding between the fiber and the resin. Okay, so I'm sorry I had to rush through, but all of these led to significant improvements in the mechanical properties, both static and dynamic. I'd like to thank my former students, Dr. Byung-Ju Kim, Sang-Hyuk Cha, and Dr. Bom-Gon Cho, who worked on these projects, and also my current student, Yoon-Bo Shim, who is in the third doctoral year. With that, I'd like to close my talk, and I'd like to thank you all for your attention.
Yeah, thank you, Professor Park, for your enlightening talk. It's me, Kusum. Can you see me?
Yeah, I can see you.
Yeah. So thank you very much for being part of this conference. So now I request any of the participants, if you have any queries, you can talk to Park. So I need to know one thing. What are the applications that you are basically making with this composite material?
So I think these are, for now, aerospace would be one good application, or maybe defense. But as for automotive, mass production, where the economy is important, where the cost saving is important, these may not be appropriate right now, but eventually I'm hoping that these will apply to any applications where lighter and stronger materials are required. But cost would be an issue, definitely.
Yeah, can I ask a question to Dr. Park?
Sure.
Yeah, hello. This is Ranga Rao from IIT Madras,
Hi.
south of India. You are actually, now the conference is conducted in northeast of India. It's almost 1200 kilometers, 1300 kilometers away from me. But anyway, this has brought us, together. My question is that, you have mentioned about graphene hydrogels. You have not presented any data, but I'm interested in that area. If you are, if you can share some information on that. Have you made the graphene hydrogels and then measured how much water it can store and what are their properties, etc.?
Our target was a sensor. It's a physical sensor that could measure the pressure, compressive compression. So in that, maybe I can go back here. Okay, so this one, right? Yeah. So here, basically, it's a very, very, very simple and basic concept called piezo resistivity. So if you measure the change in electrical resistance as you apply compression as shown here, then because the hydrogels are so compressive, they have a very high sensitivity in terms of the under compression. So we particularly looked at the mechanical compression measurement. I have one paper published on this topic, and if you email me, then I'll be more than happy to send it to you.
Okay. Thank you so much. I'm interested in hydrogels. That's why I asked the question.
Okay. So if you need my contact information, it's
I think I have your email. I will note it down somewhere.
Here, that's good. Okay.
Yeah, here. Yeah, I have noted it down. Yeah.
Okay. Thank you for your question. Thank you.
Thank you. Nice work. Good. Thank you.
I presume there are no more questions. So Dr. Ilyas said Ismagulov was unable to present due to some technical glitch, but now he's back with us. So I would now request Dr. Ilyas said Ismagulov, sir, to kindly present his talk. Dr. Ilyas said Ismagulov is currently associated with Boreskov Institute of Catalysis, Russia. His research domain mainly focuses in the arena of environmental catalysis. His skills and expertise lie in the field of computational fluid dynamics, XRD development of novel catalysts, etc. With this, I would now request Sir to kindly present his talk. Sir, you may begin your presentation.
We can't hear him.
Sir, you are kindly requested to start your presentation. Sir, you are not audible. The slides are visible, but you are not audible. Dr. Ilyas Ismailov is once again facing some network issues, so we will move on to the next speaker. Next, we have with us Dr. Suman Lata Jain. She is a senior scientist and head Synthetic and Applied Chemistry Area, Chemical Science Division, CSIR, Indian Institute of Petroleum, Mohampur, Dehradun. Dr. Jain's research domain specializes in the arena of utilizing of carbon dioxide for fuel and value-added chemicals, photocatalytic reduction, green chemistry, cost-effective, environmentally benign multifunctional additives for lubricating oils, value addition of refining streams, etc. She pursued her PhD in chemistry in synthetic organic chemistry from CSIR Indian Institute of Petroleum, Dehradun. She is an AVH Humboldt Fellow at University of Regensburg, Germany, a research associate at CSIR Indian Institute of Petroleum, Dehradun. She has many credentials to her credit. She is selected for CRSI Bronze Medal 2017. She has been awarded INSA Professor D.S. Kothari Chair Award 2017-18. She has been also awarded SERB Women Excellence Award by DST 2013. She is also awarded CSI Young Scientist Award 2010. With this, now I'd request Dr. Jain to kindly resume her talk.
So, how can I share my presentation, because I'm unable to see that share content is not visible here, no? Am I audible?
Yes, ma'am, you're audible. Ma'am, you can try it now.
Yeah. So I have to share the screen. No?
Yes, ma'am, it's visible now.
So are you, is my presentation is visible?
Yes, ma'am.
Okay.
Yes, ma'am.
So, yeah, thank you so much for the kind introduction. So first of all, I would like to thanks to organizers of ICMCC 2021 for giving me this opportunity to present my research work here. And I'm also attending the conference since last one day. And I'm very much impressed with the quality of presentations, and I'm glad to have excellent presentations by the eminent researchers, both nationally and internationally. So I would like to talk my research. Mainly we are working on the visible light driven conversion of carbon dioxide to chemicals. Mainly we are using the molecular hybrid materials. So these are the contents of my talk. First of all, I would like to give the introduction, like why we need to do, means why it is required to mitigate the CO2, what are the problems, what are the challenges, and how we can mitigate, and what are the future perspectives in this area. And although as we know that a lot of fundamental research has been done in the CO2 utilization area, but still we are very much far away from some practical applications. Only very few industrial processes are known having the use of carbon dioxide as the feedstocks. So what are the main barriers behind this? I would like to give a glimpse of this. And then I come to my research topic, that is photocatalytic reduction of CO2. I would like to discuss my recent findings which we are carrying out in our lab, and some of the novel ways which we are working currently. And with this, I will conclude my talk. So first of all, as we know that energy and environment, these are the two important issues of this era. We are far moved from that pre-industrial area to the highly developed area. So with this development, although we have changed our life or improved our life a lot, but with this development, somehow we have forgot about environment. So with this development, one of the main thing is that in carbon dioxide concentration is also increasing in the environment. And this increasing concentration of carbon dioxide is having the adverse effect on the environment, that is called the global warming. So with this higher concentration of carbon dioxide, not only the global warming which we are facing the climate changes, and also the aquatic life has also changed, because as we know that carbon dioxide is an acidic molecule and it has the solubility with water. So when it dissolved in the water, it formed the carbonic acid. So the acidification of the oceans, like pH of that ocean is being acidic. So this change in the pH is changing the aquatic life, as well as the climatic changes due to the global warming we are facing. So these are the main issues. Due to that, we need to understand the challenges. We need to understand why we need to mitigate the carbon dioxide. why it is an urgent need of the present situation. So these are some approaches. By using those approaches, we can reduce the carbon dioxide. First of all, if we can reduce the carbon dioxide production. So as far as I concern or I understand this, it is not in our hands now, because we cannot go back into the pre-industrial area. So we are developing and we will be developing. So the reduction of the carbon dioxide production is not in very much in our hands. Another approach is we can capture this carbon dioxide and we can store it. So this is the general phenomena. We are capturing the carbon dioxide and storing it in the underground regions. But the capturing of carbon dioxide, its transportation, purification, and finally the storage, all these steps have a lot of cost involvement. So this is a highly expensive process. And another problem is that if we are storing the carbon dioxide, like in the deep ocean, deep saline region or geometrical form, whatever, in the underground, if you are storing it, there is always a chances of the leakage. So if something accidentally, any leakage happen, it will create a more problem to the environment. So we have to think about a viable solution to what we can do. So whatever the next or most promising approach is the carbon dioxide utilization. As we know that carbon dioxide is a inexpensive and C1 molecule. So it can be used for the formation of any carbon molecule or means any industrial chemical by with the use of carbon dioxide as a feedstock. So among all these approaches, this is the most viable. Here we are not just dumping a waste product. However, we are seeing the value of a waste product, and we can use the carbon dioxide as a valuable feedstock. So this is my research area. These are some future perspectives of the CO2 utilization. If we look at the today, although some of the industrial processes like conversion of carbon dioxide to urea, salicylic acid, ethylene carbonate, so on and so forth. So all these processes are just thermal. We are using the thermal catalysis method, or we are giving the energy in the form of high temperature or whatever to get the chemicals from the fuel. If we look at the short-term scenario, in the current area also, in the current years also, the algae is being used for the mitigation of CO2. So if we look at the short-term perspective of the CO2 utilization, we can produce not only chemicals but also fuels from the CO2. So similarly, in the medium-term scenario, we can use not only the thermal processes, however the electrochemical routes, algae routes for the production of chemicals as well as fuels from the carbon dioxide. However, in the long-term approach, or if we see our future in the CO2 utilization area, there are a lot of approaches. It is thermal. We can use electrochemical, photoelectrochemical, photocatalysis, algae for not only the production of chemicals, but also for the production of fuel in a large amount. So this long-term approach can provide a viable solution by that we can convert a significant amount of carbon dioxide to the fuels or valuable chemicals. And by that way, we can convert a waste product to a value-added chemical. So, but as we know that a lot of procedures or lot of fundamental research is going on in the CO2 utilization area, but still technological developments are very, very, very less. So what is the reason behind it? As we know that CO2 is a highly stable molecule. So breaking of the bond requires an extensive amount of energy. So this thermodynamic and kinetic stability of the CO2 molecule itself is a very, very big problem. So we need to give a higher energy for the chemical conversions. Similarly, the cost of CO2 capture, because CO2 amount of the CO2 in the atmosphere is very, very less. It's only a few ppm. So the capturing of the CO2 from the atmosphere or from the source and its separation, purification and transportation, it needs or it involves a huge amount of expenditure. So all these steps are involve the cost. So they are cost intensive processes. Similarly, we know that all the chemicals are mainly based on the Fischer-Tropsch synthesis, where carbon monoxide used as a C1 feedstock. So industrial commitments are very lack. like industries, they don't want to take the challenge from, or they don't want to take the risk from switching off the carbon monoxide to the carbon dioxide. So these are some drawbacks. Similarly, the social economic, because the CO2 research is at only the fundamental step or fundamental stage. We do not know about what is the basic what is the economics of the use of this carbon dioxide. If we are producing some chemical using the carbon dioxide, it is economically viable or not. Or the another chance is that we are using the CO2, but at the end it may be we are producing the more CO2. So these are some challenges, these are some barriers which make us think about how we can use the carbon dioxide, or how we can overcome these challenges. As I said earlier, that CO2 is a C1 molecule, so any chemical that we can think of, we can produce from the carbon dioxide. Like either it is alcohol, acid derivatives, carbonates, inorganic carbonates, any compound that contains C1 or carbon atom, we can produce from the carbon dioxide. But it is not as simple as it depicted on this graph. The main problem is the stability of the carbon dioxide that requires a lot of energy. So our approach, what we are doing, actually, we are dealing with the photocatalysis. Photocatalysis is the material that absorb the light and enhance the reaction in the presence of light. So if we know that solar energy is abundant, it is clean energy, exhaustible, inexhaustible. So if we can use the solar energy for the conversion or for the activation of carbon dioxide, then we can have some viable solutions for the use of carbon dioxide for the chemicals or for the fuel area. So this is the basic picture how a photocatalyst works. As a material, this is the photocatalyst. Under the light irradiation, the charge separation takes place. The electrons when the material is absorbed the light, the electrons from the valence band migrate to the conduction band, and the hole formation occurs at this valence band. And these electrons are used for the reduction of carbon dioxide to chemicals or fuel. However, to satisfy these holes, we need to have oxidation of water or any other organic compound or organic chemical to complete this photoredox cycle. So the basic requirement is that the band gap of this material should be compatible with this light irradiation. So lot of semiconducting materials, lot of heterojunctions, and in the literature, if we see plenty of materials have known for the photocatalytic reduction or photocatalytic conversion of CO2, but still some of the drawbacks or some of the limitations are, as I said, like under the light absorption, the charge separation takes place. As the electron and hole separates, immediately they recombine. So this is called the electron and hole recombination. So one drawback is that the recombination of electrons and holes takes place very fast. So the availability of electrons for the CO2 reduction is lower. So due to these some reasons, the photocatalytic reduction or conversion of carbon dioxide to fuels under the light irradiation is low, and the selectivity of product, this is the potential that we require. Carbon dioxide, if it requires 2 electrons, it can give formic acid. Similarly, if it requires the 6 electrons for the reduction, the desired product is methanol. So the selectivity of the products as well as the conversion of the CO2 to the desired product, both are the challenging tasks in the current scenario. But this technology has a wider scope because there are 2 reasons for this its importance. One is that we are using the solar light for the activation of carbon dioxide, and another one is that the reactions are being carried out under the atmospheric pressure and ambient temperature conditions. In otherwise, if we look at the thermal conditions or thermal catalysis, we need to provide a higher temperature to activate the carbon dioxide molecule. So this is in the literature we have seen that a lot of number of semiconducting materials have been reported for the activation of carbon dioxide. So this is that is the general phenomena only. Under the light radiation, charge separation takes place. Electrons are used. Electrons which are in the conduction band are used for the reduction reaction, and holes which are in the valence band, they are used for the oxidation reaction. But if this band gap should be compatible with the visible light. Why visible light? Because we know that in the solar light spectrum, only 5% is the UV light, and more than 45% is the visible region. So to make the effective use of the solar light, we need to design the material, or we need to develop the materials that can absorb the visible portion of the light, so that we can develop some technology, or we can develop some good materials for the effective use of the solar light for the photocatalysis reactions. So for this band gap should be compatible. If the band gap of the semiconductor is higher, it can work only in the UV region. It will not work in the visible region. So these are some basic fundamental aspects or some challenges behind the materials or behind the research that has been done or is going on in the recent years. So we are mainly working on the homogeneous metal complexes. In the last two slides, I showed some semiconducting materials. Some of the materials are quite effective because a lot of modifications has been done in the recent year by doping some co-metals, by doping some, by sensitizing with dyes, and by combining two of the semiconductors, or by the band gap engineering, so that the recombination rates can be inhibited and the visible light can be absorbed for the effective use of the solar light for the photocatalytic CO2 conversion. But why we are mainly interested to the metal complexes? Because we are mainly interested in those kind of complexes. These are the halocyanins, porphyrins, and polypyridyl complexes. Because these nitrogen containing ligands, they have the effective electron density on the metal. So this metal can bind with the carbon dioxide molecule, and this binding increases the concentration of the CO2 at the catalyst surface or at the in the vicinity of the metal complex, and this increased concentration obviously provides the higher conversion and the selectivity of the product. As we can see that a lot of unsaturation is there in the complex. So due to this unsaturation, these complexes are visible light active. They absorb the light into the visible region. So therefore, we have chosen these complexes as our best candidates for the photocatalytic CO2 reduction. So we are mainly working on the homogeneous complexes. But as we all know that homogeneous complexes, they have some obvious disadvantages, like they are less robust because they are soluble in your reaction mixture. So there is always a possibility to photodegradation of these complexes or ligands, because complexes, they are containing a lot of organic ligands. So there is a possibility of photodegradation of these molecules. And due to the homogeneous nature, they are very tedious in recovery. We cannot recover it very easily. And one of the major drawback is that we need to use sacrificial electron donors to complete the electron density or to complete the photocatalytic cycle when we are using the homogeneous complexes. So to overcome this limitation, we have chosen, or we are working on the transformation of these complexes to the heterogeneous forms by immobilizing these complexes to the semiconducting photoactive supports. So what are the advantages of this approach? By this way, when we are immobilizing our complexes on the photoactive supports, we are making the something is heterogeneous to the homogeneous to the heterogeneous one. So it provided the benefits of facile recovery as well as the recyclability. Similarly, when we are using the photoactive supports, we are increasing the photocatalytic activity, or we are increasing the visible light response of the catalyst. These immobilized systems showed the increased efficiency. They are highly robust, stable, because immobilization enhances the stability of the molecule, complex molecule. And by changing the metal, ligand and support, by this combination, we can tune or we can design our photocatalyst to get the desired product. And one of the major advantages is that we do not need to have sacrificial donors with these kind of hybrid systems. So actually, when I am saying that these hybrid systems are superior than the semiconducting materials, how? in the semiconducting materials, we say that when charge separation takes place, the recombination reactions are very fast. So these electrons and holes, they recombine and inhibit the reaction. But when we take the metal complex, this is the metal complex, under the light irradiation, charge separation takes place in the complex, and these electrons from the LUMO of the metal complex, they transfer to the conduction band. So now our CO2 is not only dependent on the electrons which coming from the valence band, but it has the sufficient electrons which are coming from the LUMO of the metal complex for the reduction. So this is the main reason why these hybrid systems are acting better or performing better, because of the availability of the electrons for the reduction of carbon dioxide is higher. So or we can say this is the antenna system. The continuous pumping of the electrons in the conduction band takes place in the presence of by combining the metal complex with this such kind of semiconducting system. So this is the basic fundamental why we are using the immobilized systems, why they are superior and how they are working. So now I will come to our research. First, the system which we have developed in our lab. Here we use the graphene oxide as the semiconducting support. In some of the literature, graphene oxide has been known as the visible light active material. So we have chosen this photoactive support for the effective immobilization or chemical attachment of the complex. Firstly, we functionalize that graphene oxide with the chloroacetic acid to enhance the carboxylated functionalities on that. And after that, it was treated with our complex cobalt phthalocyanine tetrasulfonamide to get this hybrid system. In this hybrid system, we can see the chemical attachment of the complex with our photoactive support not only provided the stability and but also provided direct connection between the support and the complex. So these are our report. Means if we look at the comparison, like this is the graphene oxide, bare graphene oxide, and this is the physical mixture of the graphene oxide and cobalt phthalocyanine, and this is our immobilized system, where our complex is chemically attached to the graphene oxide. So we can easily see the difference. This our hybrid system has significantly higher yield of the methanol in comparison to the both bare semiconducting support as well as from the physical mixture. So this difference in the reactivity also confirm that chemical attachment between the two components not only enhances the stability of the molecule but also provided a positive effect on the conversion and the selectivity of the product. So selectively we got the methanol in this reaction with a significantly higher yield in comparison to the several literatures. So how this system is work? Clearly we can see that how much effectively this system at work rather than its components. So this is the basic mechanism. In the presence of light, our semiconductor is acting as a photosensitizer, so it gets activated, it comes in the excited state. Under the excited state, it provided the electrons to the conduction band, and these electrons are used for the reduction of carbon dioxide to the methanol. However, the electrons which are moved from the HOMO to the LUMO, they are satisfied by the use of triethylamine. So in this system, we have used the triethylamine as a sacrificial electron donors. Subsequently, we have developed a number of materials where we did not use any sacrificial electron donor. Our support itself provided the electrons, and the water which we are using in the reaction that provided the necessary protons as well as the electron for the reaction. So in other reports, we have not used the sacrificial electron donors. Similarly, this is another work which we carried out in our lab. In previous work, we used the cobalt phthalocyanine. In this, we have used the ruthenium-based polyprydyl complex with some heterolactic ligand. Two kinds of ligands we have used to design this complex. Similarly, again, we use the graphene oxide as support. First, before the immobilization, we functionalize the support for better connectivity or better chemical attachment between the two components. And this is our hybrid. This is our hybrid system. Sorry, containing the graphene oxide support and highly immobilized and with the ruthenium complex. So again, if we look at the results, This is our hybrid system, which is providing a significantly higher yield of the methanol in comparison to the various combinations. Either if we can compare with the bare complex, we can compare with the physical mixture, we can compare with the functionalized support, or we can compare with the bare semiconducting graphene oxide support. So among all the combinations, our hybrid system provided the better efficiency, better yield of the that methanol from the carbon dioxide, and higher stability. We can easily recover it after the reaction, and it could be reused for at least 4 or 5 runs that we checked in our laboratory. So mechanism is similar. Under the light irradiation, that excitation of the molecular complex takes place. Electrons undergo to the conduction band, and one of the important parameter is that unsaturated support, it provides the higher electron mobility. So due to this improved mobility of the electrons, the recombinations of the electrons and holes is diminished, or carbon dioxide molecule has the higher electron availability for its conversion. So subsequently, we have done a lot of research on development of hybrid systems. These are our some publications. So with this research, we concluded that photocatalytic reduction of carbon dioxide into the fuels or important chemicals like methanol is feasible, and it is advantageous. We can develop some systems other than the semiconducting materials if we combine both the systems. If we combine the semiconducting materials with the metal complex, we can increase the performance of the material as well as the selectivity of the product. So this is the next work which we are performing now with the use of CO2. We are working on the carboxylation reactions. As we know that carboxylic acids they have a huge market, and the market is continuously increasing, mainly due to the lot of applications of the carboxylic acids. They are used as a precursor in the pharmaceuticals, dyes, plastics, so on and so forth. So due to these multiple applications, carboxylic acids are very, very important building blocks. Conventional approach for their synthesis involves the use of carbon monoxide and molecular hydrogen. The use of carbon monoxide is undesirable due to its obvious disadvantages, like it is toxic, it is not safer in handling and transportation, etc. But carboxylation of olefins using CO2 is advantageous because carbon dioxide is inexpensive, easily available, and safe and non-toxic. So carboxylation of olefins or any other unsaturated compounds is advantageous, but so far only thermal catalytic methods are known for the carboxylation reaction. Those known thermal methods, they have certain drawbacks. The main drawbacks are they are using the stoichiometric amount of organometallic complexes, they are using the co-catalyst, and obviously, like other thermal processes, the reactions are being performed under the higher temperatures. So to overcome these limitations, we focused our attention on the use of photocatalysis. Photocatalytic carboxylation is rarely known, and before starting this work, we could find only one report that uses the rhodium-based homogeneous complex for the hydrogenation, for the carboxylation of the such olefins, aromatic olefins, by using the ruthenium photosensitizer. So in this, not only the carboxylated product, but the byproducts, that is hydrogenated byproducts, are also formed. So this was the only report before our work. So during our work, we developed a nickel oxide, nickel-based photocatalyst for the carboxylation of olefins. And one of the key advantage of this process, we could get only selectively the carboxylic acids without any evidence for the formation of any hydrogenated product that were reported in the literature. So with this, we developed a nickel-based system. This is the nickel oxide support. This is the ruthenium-based photosensitizer. So again, this is the hybrid material. Under the visible light irradiation, excitation takes place and electrons come in the conduction band of the semiconductor, and they are used for the generation of this anion radical. However, at the valence band, oxidation of this olefin takes place to give this cation radical. The coupling of these two radicals in the presence of dimethyl acetamide DB, that is the CO2 philic solvent, it absorbs the CO2. So we use this as a solvent. And it also provided the proton for the reaction. With this, we get the carbon dioxide, the carboxylic acids. So what are the main advantages of this? This is the sorry. Here we use the nickel-based catalyst. However, in the literature, rhodium, that is the expensive metal, so it was the cost-effective material that we developed. We immobilize the complex with ruthenium sensitizer in situ, and attachment of this inhibited the leaching. However, in the previous report, where the rhodium-based complex is used, ruthenium photosensitizer is used, but both are in the homogeneous condition, so the recovery is not very easy. Here we developed a heterogeneous system by combining both the components. So these are the facile. We could easily recover the material after the reaction, and we could successfully reuse it for at least 3 or 4 runs. A number of olefins as well as the aromatic compounds, they are successfully carboxylated or only with the formation of hydroformylated or carboxylated product. We did not get any hydrogenated products during these reactions. And one of the fascinating thing is that the reactions occurred at the room temperature as well as at the 1 atmospheric pressure of the CO2. So these are some advantages, and because nickel has the magnetic nature, so we could easily recover the catalyst through the external magnet. Our recent finding, it is the very, very breakthrough work which we recently carried out in our lab by using the methanol, conversion of the methanol, carboxylation of the methanol to the acetic acid. As we know that acetic acid is like among other carboxylic acid, in the most of the carboxylic acid, acetic acid is the one of the component that is used extensively. These are the some commercial methods. All the methods are require carbon monoxide and molecular hydrogen with some rhodium or iridium based complexes. So these conventional methods have the obvious drawbacks with the use of carbon monoxide as well as the expensive metal complexes. There are in the literature only couple of reports are known for the use of CO2 to the acetic acid, but photocatalytic method are known. This is our benchmark. This is the thermal method where rhodium based complex has been used for the conversion of methanol, carbon dioxide and hydrogen to the acetic acid at the higher temperature. So homogeneous complex was used, expensive catalyst was used, higher reaction temperature is used, and the selectivity, moderate conversion is like 60 to 70% with the 80% selectivity of this is reported. So with these drawbacks, we started our finding on the photocatalytic conversion of methanol to the acetic acid with various advantages. We used cobalt-based complex that is comparative to rhodium is very, very inexpensive. This octasulfur we used as a support for immobilization or for making this heterogeneous one. The reactions we carried out under the atmospheric pressure and room temperature in the presence of light. We got the selectivity of the acetic acid is more than 95% with the conversion 60 to 65% in the range. Main attractive thing is that we did not use any sacrificial electron or proton donor. It's a very recoverable, we could easily recover and recycled. These are the effects of reaction parameters. We screened a number of solvents. Among all these, DMA, dimethyl acetamide, is found to be optimum one because it has a binding tendency with the carbon dioxide, so it is called a CO2-philic solvent. So it increases the concentration of carbon dioxide in the reaction medium, so that is one of the main reasons for its higher reactivity. Similarly, we optimize the catalyst dose. Among all these, we can see that 1 mole% catalyst was enough for the maximum conversion and selectivity of the desired product. If we increases the catalyst loading, we saw that it affected adversely to the reaction, mainly because it increases the concentration of the CO or COPC molecule on the support. Maybe it made the crowded, and so steric means hindrance is caused for the binding of your substrate. So that might be a possible reason for the lesser reactivity when we are using the higher catalyst dose. Similarly, these are the recyclability data. We can see that this is the fresh catalyst and this is the third run. Recovered catalyst we used for the third run. So in all the cases, consistent selectivity and conversion we obtained. So we concluded that a very lower amount of catalyst is enough for the maximum conversion. and the catalyst was nicely, it was stable. We did not find any degradation of the catalyst, and it could easily recovered and recycled up to 3 or 4 runs without any significant decrease in the activity. We performed some DFT studies to understand the mechanism. Although these studies are under progress, we are working in collaboration with Dr. Shelja in NCL, CSIR NCL. So with this, some of the DFT studies showed that connection of octasulfur with the cobalt increases the reaction in comparison to the cobalt, because the connection or attachment of the cobalt halocyanin with this octasulfur increases the electron mobility or electron density on the catalyst, overall on the catalyst. So the electron availability to react with the carbon dioxide is increases. That one of the promising or one of the possible reason for increasing the reactivity of this hybrid system rather than the bare complex. Similarly, the attachment of this density of state plots indicates that the band gap is also reduced when we combine both the components, like when we combine the octasulfur with our cobalt halocyanin, the combined band gap was reduced. This reduction in the combined band gap increases the visible light activity. So these studies and further optimization and further understanding of the mechanism of reaction is under progress through the theoretical studies. But in our laboratory, we have done a number of controlled experiments to elucidate the mechanism. So first of all, we did not find the formation of carbon monoxide in the effluent gas. So by this, we understood it is not a carbonylation reaction, it's a carboxylation reaction. Means the CO2 molecule is taking part in the reaction, not the carbon monoxide. Because we could not find or could not detect the carbon monoxide in the gaseous phase. Similarly, we observed the formation of water in the liquid phase and ethylene in the gaseous phase. So these things made us why we are getting the ethylene. So we understood carbene is being formed as a reaction intermediate and with the removal of water from the methanol. So further to confirm that formation of carbene, we used trapping experiments. We used the styrene along with the methanol, and as expected, we get the cyclopropyl benzene in the reaction that was formed in the reaction. So these some controlled experiments confirm the formation of carbene as the initial intermediate of the reaction. So by this, we propose the following mechanism. In the first step, methanol dehydration of the methanol occurs provided the carbene, and in the second step, these carbenes are very reactive intermediates, so it could form the ethylene that we detected in our gaseous phase. This carbene can react with the carbon dioxide to form this, because along with the acetic acid, we also observed the formation of vinyl acetate, cyclopropyl carboxylic acid, as well as the acetic anhydride. So with this mechanism, we can postulate all these formation of all these byproducts along with the acetic acid. So this is the general mechanism. In the presence of light, our catalyst excited and the formation of carbene occurs, and this carbene attached with this complex to provide this reaction intermediate. Carbon dioxide insertion takes place. It forms the carboxylate, metal carboxylate. Metal carboxylate is converted into the finally in acetic acid. So these are our assumptions so far. Further DFT studies and detailed mechanistic understanding is under progress. So with this, now I would like to conclude my talk. Like CO2 is a highly stable molecule. It requires extensive amount of energy in thermal catalysis. But in photocatalytic reduction of carbon dioxide, photocatalytic activation of carbon dioxide is possible with the use of solar energy. That is much more promising and viable, because it is solar energy is inexpensive, abundantly available. And so far, photoredox research has been done on the semiconducting materials, and further modifications are being carried out. But we need to think in the different direction. We can use the carbon dioxide not only for the reduction of into the C1 products, but also we can use the carbon dioxide as a C1 feedstock for the other valuable chemicals under the ambient temperature and pressure conditions, using the fascinating properties of the photocatalyst. For that, we can design our complexes or we can design our catalysts accordingly for the reaction. So our approach is to use transition metal complexes further and to immobilize or to transform into the heterogeneous forms by immobilizing them with the photoactive supports. This immobilization not only provided the higher activity or higher selectivity of the product, but it provided the benefits of facile recovery and recycling of the catalyst. So these are the fundamental research which we can pursue further, or which we can this knowledge base we can use further for developing some technological developments in the CO2 area. It has a lot of scope, and in future we sincerely hope we will develop, or we could reach to some point for the viable solution for this CO2 mitigation through this chemical fixation route. So before ending my talk, I just would like to request to all participants to encourage your students, to encourage your faculty members to to publish your work in the New Journal of Chemistry. I am an associate editor of this journal, and this is a very good journal. It is a multidisciplinary journal. They accept all the papers in the chemistry as well as all the associated fields. So I request to all researchers, you encourage your students to publish in the New Journal of Chemistry. This is the Journal of Royal Society of Chemistry, and I am serving as an associate editor since 2018. So last but not the least, I would like to acknowledge the organizers of the ICMCC 2021 for giving me this excellent opportunity to present my research work. Our director for his kind permission, Dr. Shelja Krishnamurthy, CSIR NCL, for providing DFT studies, CSIR New Delhi for financial assistance of this work, my PhD student, Ms. Sandhya Saini, who is working on the carboxylation using CO2, so all the experimental work she is carrying out, and my research team. So with this, thank you all for your kind attention. Thanks.
Thank you, ma'am, for your informative talk. The session is now open for questioning purpose. If anyone is interested to ask question, you may unmute yourself and ask.
Yeah, can I ask Dr. Suman Lata?
Yes, sir.
Yeah, that's very interesting talk. I'm really excited to say listen to you. A couple of just experimental questions, details I want. When you're doing this, what kind of a reactor have you used for this homogeneous photocatalysis?
So basically, we are using a very simple photoreactor. We are just using a Borosil container of 60 ml or 50 ml, like a beaker or some vessel. It's a purely glass, and we are using 20-watt LED lamps which are readily available in the market. So it's a very in-house made, very easily fabricated system which we are using in our laboratory for these batch kind of reactions. But recently we have started working on the flow reactors. So we have fabricated with our own design a photoreactor of 1.5 liter capacity. So some of the materials which are giving excellent results in our batch reactions, we are performing the scale up, or we are doing the scale up on our higher capacity photoreactor.
And then CO2 and chemical, the detection of the products, which can be in the gaseous form, or some of them can be in the liquid form. Are you doing this gaseous products online GC, and then how are you analyzing the products in the liquid phase?
So in the liquid phase products, we are mainly analyzing by the GCFID, and in the gaseous phase product, we are analyzing by the refinery gas analyzer. In the IIP, we have quite well-equipped facilities for these gaseous detection and the liquid product detection with this gas chromatographic method. So we are having good facilities in our institute. So initially we are monitoring the reaction through the GCFID and RGA. Gaseous products we are analyzing through the RGA, and liquid products we are first we are seeing the GCFID, after that GCMS and HNMR.
So is it online, or you just take the sample and then?
No, sir. It is offline. It is offline.
Oh, it's offline. Okay.
Because in the because we are performing the reaction in the liquid phase, not in the gaseous phase. So it is very difficult to have the system with the online measurement system. So we are collecting the samples, gaseous samples we are collecting in the Tedlar bags or in the syringes, which are provided by our GC section. And in gaseous phase products, we are simply taking the samples and analyzing through the GCFID, which we have in our lab.
Okay, thank you so much. Very nice work. Very nice.
Thank you, sir. Thank you.
Any more questions on board? I guess no. So thank you, ma'am, once again for your informative talk. We shall now move on to the next. We shall now move on to the next speaker. We have with us Professor Jayanta Chaudhary. He is currently associated with at Department of Chemistry, IISER, Bhopal. Sir's research domain mainly highlights carbon dioxide capture and utilization, developing new generation smart catalyst for energy storage and delivery, reversible hydrogen storage and delivery, organic electronics and nitrogen doped nanographene. Sir pursued his PhD from IIT Kharagpur and he pursued his postdoctoral studies from the Scripps Research Institute, Jupiter, Florida, as a TSRI postdoctoral fellow and the Weizmann Institute of Science, Israel, as a Marie Curie International Incoming Fellow. He has many credentials to his credit. He is in the editorial advisory board of ACS CATALYSIS. With this, I would now request Sir to deliver his talk.
Yeah, thank you. Can you allow me to share the slides? Am I? Yeah, fine. Okay.
Yes, sir. So you may try now.
Yes. Yeah. Just I'm getting 1 minute. Can you see my slide?
Yes, sir. It's visible.
Okay. Yeah, first of all, thank you, and I must thank the organizer team for inviting me to give a talk here in this nice international conference. And of course, yesterday also I enjoyed a lot, and of course I'm enjoying today as well. So first of all, before starting, let me switch on my timer, because that is something very important, otherwise I'll shoot my time. So I have 25 minutes plus 5 minutes. So I just switch on my time. Okay, so today I'll be talking about one of our research areas, which is, I have given a title like Sustainable CO2 Conversion Catalysis. This is only one area. We have several other areas also, but today I decided to speak about this one in this forum. Now let me, because it is an international conference, just I'll spend a couple of, just a minute. So we are, one of the 7 cluster institutes in India, and we are located here. This is IISER Bhopal. These are the IISER are the kind of cluster institutes. This is for all the foreign delegates, and we are located throughout the country, and we are in the middle. So we have a beautiful campus here in this central part of the country, and within very quick time we have been established in 2008, and within very quick time we had marked in the area of chemistry globally, and this is what we have achieved a rank of 12 in the 50 young universities in chemistry in the Nature Index 2019. So this is something that we feel proud of, and we are trying our level best to accelerate even better. So that's all with the institute where I am working, and this is my group. As I told you, I have several research focus in my lab, but central of all this research area is organometallic chemistry, and specifically metal N-heterocyclic carbene complexes. So we design ligands, and we design metal N-heterocyclic carbene complexes for certain purposes. And those purposes are mostly involved in working with small molecules, small notorious molecules, which are not easy to react, which are not easy to functionalize, and so on and so forth. And several of them are written here, like carbon dioxide, hydrogen, and lots of arene molecules, heteroarene molecules, of course alkane as well.
Sorry to interrupt you, sir. The slides are not moving, they are static.
Oh, okay. Let me check. So is it now going on?
Yes, sir.
Like here? Yeah. So I think it's moving now. Is it?
So please try once again.
Okay, okay. Okay, so let me share it again once more, right? Or is it moving? Can you just confirm me once more? Is it moving or not?
It's not moving, sir. It's on slide number 2.
Okay, okay, okay. So I think I have to let me share it once more. I'm sorry for this technical glitch. Because of this, one way we have advantage, we can do online meeting, but at the same time, we have this problem as well. Can you see my slides now?
Yes, sir, they are visible.
Okay, now is it moving?
Not yet, sir.
Not yet. You don't see the next slides, no?
No, sir. It's in the introduction slide itself.
No.
Yes, sir. I guess it's on excessive carbon dioxide emission, that particular slide. Okay, sir.
Full screen. Yeah. Is it okay? Visible?
Yes, sir. They are visible.
Okay. I hope it will be fine now. So as I was telling that we are mostly working on metal N-cyclic carbon complexes, organometallic chemistry of these complexes to target these small molecules so that we can functionalize these not so reactive molecules into some useful products. Of course, there are other areas of application of this N-cyclic carbon complexes in our lab. But today I decided that I will focus on this particular area where we are actually trying to address the H2 storage, reversible H2 storage and delivery in terms of chemical compounds, which we normally call as liquid organic hydrogen carrier. These are some sort of energy storage, but not physical energy storage, but in the form of chemical bonds. So this is one of the targets that we are pursuing in our lab, and then next is CO2 conversion as well. It has a dual purpose: CO2 conversion to alternative fuels, as well as CO2 as a kind of vector where to transfer the hydrogen energy into the application part. So this is what we are doing, and today, as I told you, that I'll be talking about a little bit about the CO2 research that we are doing. Of course, in the previous talk, we have nice introduction and a very excellent talk. So I'm not going to again introduce those things. Just a couple of seconds, I would like to focus that in the 2018 IPCC special report, this is international, panel for climate change. So this is some sort of intergovernmental, committee which they look after this climate change issues. So this is something which is very much alarming, and they noted that by 2030 we have to reduce the human caused emission of CO2 by about 45%, and 2050 we have to have a kind of net zero emission. So this is something, a very alarming situation, and a reason everybody knows. The reason is nothing but an excessive concentration of CO2, which even now it is more than 400 ppm. This is a recent data, 415 in this year itself.